Hello, everybody. Welcome here on this platform and welcome in this series also. So, fine, guys. Again, in our earlier sessions, we have discussed about various topics like as a feed forward connection, backward propagation, how learning is going to be happen inside a neural networks. And again, guys, we have also seen various, multiple activation functions available inside deep learning. We have also seen about various cost functions available in the terms of deep learning, right? And again, along with it, so we have also discussed some of the vanilla versions of optimizers in deep learning, like as SGD, MBGD, BGD, right? So batch gradient descent was there, mini batch gradient descent was there, and SGD was there, right? So guys, these were the vanilla versions of optimizers, and now today in this topic I'm going to just continue from that particular point, right? Okay, fine, guys. So first of all, before starting today's session, let's like this video, and if you are new here, please try to subscribe the channel and share its link with your friends and other peoples, right? Okay, so fine, guys. Now try to move forward in this section, right? And we will be going to discuss now some more topics in terms of optimizers, right? So guys, as in a previous session, we have discussed about this vanilla versions, right? So the batch gradient descent was there, stochastic gradient descent was there, mini batch gradient descent was there, right? And I have discussed about each and everything, how these things are varying with each other, and how these things are going to update. So see guys, whenever we can talk about a batch gradient descent, so in a batch gradient descent, this is the equation, this is a differential equation which they are going to use for updating the weights, right? So this is a theta, right? So theta means nothing. So theta means, again, in a research paper, whenever you are going to read the research papers, so inside a research paper people have written this theta, right? This theta is for notation for parameters. So whatever parameters we are having, so for each and every parameters we are going to follow the same procedure, same equation, and this will be the pattern. So theta will be what? So theta will be theta minus eta, right? This is theta and this is eta. So theta will be, again, so here I think theta new will be theta old minus eta into delta theta into j theta, right? So what is this, guys? Whenever we can talk about these things now, so see here, this is j theta, and j theta is defined as a function of theta, where this j theta is known as loss function. So whatever loss function or cost function we are going to use inside our network, or maybe inside that layer, so this is the loss function, right? And in a general way we can just denote the loss functions with j theta. So this will be a loss or cost function. Now this will be delta theta. So delta theta means what? So delta theta means that differentials of this cost function. So we are going to calculate the differentials of this cost function, and then we are going to multiply this particular thing with our learning rate, eta. This eta is the learning rate which will try to control the learning, which will try to control the updates. And then we are going to multiply both of them, and after multiplying the product we are going to get, this particular product is getting subtracted from the older weights, means theta old, and after subtracting the difference I am going to get, that particular will be our newer weights, or with the newer values of that particular parameter, right? So in that case, guys, in terms of a BGD, so theta new will be theta old minus eta into delta theta into j theta, and this type of equation they have given. Now in terms of a code implementation, so again, using a core Python, you can go in this way. So for I in range, right, num epochs, grad will be evaluate grade, loss function, data, params will be this one. So again, the same thing, guys, we are trying to do here, right? So params means what? So params means parameters, so parameters old, and learning rate. So learning rate will be there, it would be any kind of maybe a numerical value, right? And this will be grad, maybe your I can say your gradients, right? And then in that way, guys, you are going to calculate this parametrical new values, right? So this will be the code implementation for BGD if you are going for a core implementation. I mean, if you are going to implement these things in a core Python, right? Now you don't need to have this much kind of this much kind of things inside your code, because again each and everything is already available in terms of maybe a TensorFlow or in a Keras. So you just have to call their libraries, you just have to call their classes, just their functions, and in that way you are going to utilize them as well, right? Now if I can talk about SGD, so in SGD we are going to we are just going to pass a single record for each time. So here j theta will be fine, each and everything will be same. So theta new will be theta old minus theta into delta theta into j of what? So j of not a single theta, but here theta will be there, but again here x and y will be going through each and every iterations, I will be iterations, right? So for a first iteration, here I will be 0, I will be 0, so x0 y0. So in that case this will be the first record, I will be 1, this I will be 1, so second record, I will be 2, I will be 2, so third record. So in that case we are going to pass each and every single iterations at any point of time, and in that way we are going to calculate their cost functions, I mean a loss function for a single records, and then we are going to calculate their changes, differentials, and in that way guys we are going to calculate our newer weights, right? And for maybe a code implementation for SGD, we can go in this way. This will be the raw code implementation. I don't know why this file is not, actually maybe there would be some kind of issue, that's why this is not going to be open, but just see what is the issue here. So I think why it is not opening, images slash sgd.png, what is the problem? Oh, there should be some kind of problem again. Okay, so these were some kind of minimal problems guys, that's why actually I was not giving you this notebook, and I have to fix all of those issues, and then I was thinking for sharing this particular notebook. So again fine guys, there is no any worry, I will be going to fix all of those issues, and then I will try to upload these things over my GitHub repo, right? And then you will be able to get a very smooth and clear cut kind of notebook, right? Now guys, in terms of implementation for SGD, you can go in this way, but again its class will also be available there in TensorFlow or maybe Keras, you can use directly. Now in terms of MBGD guys, in MBGD we are going with one iteration, this will be 1 and this will be I plus n, right? So in this case what is happening, so maybe there will be a minimum, there will be a maximum, so you can try to set the number of records into a mini batch, and that mini batch will be passing through each and every iterations, and you are going to calculate your loss or cost on basis of that particular batches, mini batches, and then you are going to calculate their differentials, and then multiplying with the learning rate, and the same thing is going to happen. Now for MBGD the code implementation is there, you can try to use directly, but again if you are not using it directly, just going with the there, just try to import these things from their classes, right? Or maybe from TensorFlow or Keras. Now guys, there is one another very good method, that is a Newton's method. So again people generally ask in the interviews that okay fine, so what are all optimizers you are aware about, right? So they will just try to ask these questions directly, so what all optimizers you have used. So in that way guys, you will be able to you will try to tell okay fine, so I have used BGD batch gradient descent, MBGD mini batch gradient descent, SGD will be there, right? But again there is again a fourth one, right, which is known as a Newton's method, and this has been proposed by Newton is a very famous name, popular name in for mathematics and physics, and this Newton is very much famous again in physics. He have giving some law, so Newton's law we have to study in terms of a gravitational pull, right? So guys, in that term Newton is a very famous man, and again he is giving some kind of maybe contribution in this way, and again there is a method that we are going to use inside this optimizer section, right? So guys, this Newton's method is a kind of a iterative way to find out the differentials of any quantity unless and until it is not going to be a constant or zero. So what Newton is saying? So Newton is saying that here calculating double derivatives. So see, this will be xk because this will be your newer weights and this will be your older weights. I mean, k will be the iteration, so k will be current iteration, k minus 1 will be your previous iteration, and in that way it is saying that your iterations or maybe your weights will be similar, or it is going to be dependent upon this particular ratio, right? And what is this? So this is the ratio of their differential. So f dash x, fx is what? Fx is the function of x, right? But f dash x, this is dash, so f dash x, so f dash x denotes the differential of function or differential of fx, and f double dash x, so f double dash x says that it's double differentiation of x, right, or fx. So here calculating double derivatives, we are converging in a more amount, right? So Newton is saying that here we are not, see, whenever you are going to calculate BGD, MPGD or SGD, in that case you are just going to do a single derivative. But here in terms of a Newton's equation, Newton's method, you are going to utilize a double derivative way, and this double derivatives way you are going to, so they are saying that okay fine, so calculating the double derivatives we are converging in a more amount. So this is what the advantage that has been used inside Newton's method, where we are trying to do a smoothing. Yeah, we are trying to do a smoothing as well as trying to find out the gradients, not only just on the basis of first order derivatives, even based on second order derivatives, and finding out the new positions of weights and biases again. So yeah, so see, in each and every previous equations we were just trying to calculate the first order derivatives, but no, Newton is saying it is completely fine, we are trying to calculate first order derivatives, but again if we are going with a second order derivatives, then in that way we will be able to converge more and more, and in that way it will be more suitable for us in finding out the new positions of weights and biases, and I think this will be a very good way. So I think, see guys, whenever we can talk about a AI, so there is no any hard and fast rule. You can try to implement each and every way what you think, but unless and until that particular experiment is not giving you a fruitful result, you can't include them, right? So Newton was the same, Newton was doing the same thing. He have he have given some kind of a hypothesis, he have made some kind of hypothesis, and that particular hypothesis he have proved, and then in that way guys, maybe in some of the research papers you are going to get that this particular Newton equations has been used as optimization as an optimization algorithm, and that's why you should also be aware about that. Okay fine, so there is another way to find out the new positions of weights and biases, and that is the Newton's equation, which will try to calculate the double derivatives, and in that way we will be able to calculate these parameters, right? So again, if you are going to ask sorry, if you are going to elaborate these things in front of your interview viewers, so in that case I think it will be much more beneficial. Maybe you will be able to make some kind of impression. So in that case this is also very necessary. So yeah, again, for a much more detailed elaboration about this Newton's method, try to click over this link, right, and try to study all of those things. Now guys, people were just going with BGD, MBGD, SGD, but again using these all vanilla versions of optimizers, they are going to face some kind of issues. They were having 3 and 4 different kinds of optimizers, but again they all were facing some kind of issues, and they were not they were not able to calculate all those parameters in a much more smoother way. So guys, what people have did, so people were thinking about doing something new. So then a concept of momentum comes into picture. Now if I can talk about this momentum, so this momentum, are you guys having any idea about this momentum? Anybody? Hmm? I think this momentum we all have studied in our physics classes, right? Maybe in our 10th class, 9th class, maybe 11th or 12th classes, right? So momentum is a term that we have adapted from the physics class, and the same thing we are going to utilize inside our deep learning, inside our optimizers. So what is this momentum and how actually this is going to benefit you, how this is going to, people are going to utilize these things. So okay, fine, try to make some kind of focus. You see, here suppose I am going to kick a ball from a surface on a height edge, right? So again, fine, we are standing here, maybe over ground, or maybe over height edge, maybe here or maybe here we are standing, and we are trying to kicking a ball, right, from a surface on a height edge. That ball will follow some trajectory, this ball is following some kind of trajectory, right, and falls down to the earth's surface. Yeah, so it is just going upward here in this case, and then it will try to come down, because of the earth's gravitational pull with some acceleration, right? So we all know from physics classes that okay, fine, so whatever things we are trying to propagate into upper direction, so there will be some kind of a gravitational pull which is getting exerted on this particular object, and then this will be getting attracted towards the earth. So this is the what all we all are knowing, we all are aware from physics classes, right? So what actually happening here, so when we have kicked up the ball, it starts getting an acceleration, right? When we have kicked up the ball, so at time t will be 0, its acceleration was 0, right? But again, after that one, from time t will be 1, this acceleration was just started, starts getting an a change, getting a kind of increment, and this acceleration causes it to increase the velocity due to the earth's gravity. And this particular acceleration will try to increase the velocity, right, of this object. Now during the fall or during the trajectory, at every point of time there will be a tangential force, right? So at every point of time in this trajectory, there will be a kind of tangential force which is getting applied, which will be applied and will try to pull it towards the earth, right? So suppose, again this is a kind of diagram, so which is not, so suppose a person is standing here and he is trying to kick out the ball from this point, and ball will try to follow this trajectory, right? So in this sequence, guys, in this sequence, whenever yeah, so which will be applied and will try to pull it towards the earth. So yeah, so there will be a kind of a tangential force that will be applied over the object, this ball, and it will try to pull it towards the earth at each point of time. Now during the fall, at every steps, it will keep on changing the velocity. So when this trajectory has been started, so at that particular point of time velocity will be less, right? But again, as it is getting progress, so with the time axis, this particular velocity is getting a kind of increment, right? Velocity is increasing, acceleration is increasing, right? And in that way, guys, we can say that at every steps it will keep on changing the velocity, centripetal velocity as well as centrifugal velocity, right? And at the same point of time it will try to change its tangents as well. Yeah, so at each and every point its tangents will be getting changed, and whenever it is going to strike on earth's surface, so at that point of time its velocity will be maximum. Yeah, fine. Now during the fall, when we used to calculate the velocities at any of the particular stage, we always try to consider the previous velocities and then calculate the new one. Now if I say, okay fine, so this ball is trying to cover this particular distance, okay, so fine, at this particular point of time try to calculate the velocity of this object, or maybe at this particular point of time try to calculate the velocities. So how you are going to calculate the velocities? So can I say that you are going to consider all of the older velocities as well in terms of calculating these velocities, right? Because here we are going to get a kind of change in maybe in terms of acceleration, maybe in terms of velocities, right? And in that way, guys, we are always going to consider our previous velocities and then calculate the new one, right? Yeah. Now people says that okay fine, so here in case of optimization we are supposed to fall into the minima, and then we'll calculate the parameters. So the same thing is going to happen in terms of optimization, guys. So far, so forth, whenever we have changed the weights, maybe in terms of any one, optimizers. So far, so forth, whatever optimizers we have seen, we have used, we have, discussed, whenever we have changed the weights, we were considering the older weights, right? And then finding out first order differentials and multiplying it with the learning rate, but the learning rate was fixed there and was not an actual learnable parameter. So see, if I can talk about your maybe your SGD, your BGD, MBGD, so each and every places your learning rate was a fixed one. It was not a learnable parameter, and we were trying to give a kind of maybe a constant kind of a learning rate for each and every parameters for getting convergence, right? And that was not a good thing. So it's a kind of a constant parameter that we are giving from our end, right? In case of all the vanilla versions of gradient descent algorithms, right? Whether it is a BGD or SGD or it is MGD or in a Newton's method, right? So in each and every cases we are trying to do the same thing, but in a further improved versions of these optimizers, people have introduced a concept of momentum, right? The same concept of momentum, which simply means that whenever we are talking about the learning rate, my learning rate will be decided based on the past learnable parameters, right? So this says that, okay, fine, so we are trying to introduce here concept of momentum, and this momentum will means that it will mean that, okay, fine, so whenever we are talking about the learning rate, so see, learning rate will be fine. Again, the same kind of trajectory, same kind of motion we are going to follow here. There is a ball which is trying to follow a trajectory to come down on the earth's surface, and here we are having an error factor which is supposed to come onto the minima point. So a story is same, right? Same story is there, and now we have to follow a kind of a learning rate. So whenever we are going to calculate our learning rates at each and every point of time, so my learning rate will not be constant. If we are going to have a constant learning rate, guys, it will be a problem for us. So my learning rate will not be a constant, but my learning rate will be decided based on the past learnable parameters. So whatever learning rate it is having in earlier iterations, earlier epochs, that particular I can say all those learnable parameters we are going to consider, and then we are going to calculate the learning rate for our current iterations. See, so this was the same thing, guys. Again, people have introduced in terms of maybe momentum based optimizers. So see what this is. So if I am trying to change the weights, and maybe if I have changed for the first time, then changed for second time, and again have changed for third time or fourth time, so from very beginning I have started with keeping a high learning rate, right? Yeah, and then decreases in second iteration, again decreases in third iteration, and again decreases further based on the learning or based on the parameter that I have tuned in earlier iterations. So here we are trying to control the learning rate with respect to the momentum. So see, here is the same concept happening, guys, because see, whatever things has been happened in a past, so we are going to consider all of those things, and then we are going to calculate our current learning rate. It's not like that we are going to just we are going to give a constant learning rate for each and every iterations, and that will be fine for us. No, in a very beginning people don't have any idea about these things, but again they were trying to introduce this concept of momentum, and according to this concept of momentum, they are trying to control the learning rate as well, and they were considering this all previous learning rates. I mean learning rates from previous or earlier iterations that they have obtained, they have learned, right? So momentum means here the new velocity will be decided on the basis of older ones, or the changes made into older velocities. So whatever see, it is saying that, okay, fine, so momentum means here that the new velocity will be decided in a terms of a physics, in trajectory. Your momentum means that your new velocity will be decided on the basis of older ones. So whatever older velocity you are having, your newer velocity will get decided upon that one, and changes made into older velocities. If changes are huge, so again our new velocity will get impacted by that. That's the reason whenever a projectile is going to follow a trajectory, every time velocity is not going to be same. It will get increasing because every time it is feeling 9.8 meter per second square acceleration and so getting pulled towards the earth. It will try to change the previous changes as well. So basically it will always try to consider a momentum of previous stages. So see guys, whenever this particular object is trying to start from this particular point and it is trying to come down towards the earth, so at each and every point its tangential force is getting changed, tangents will getting changed, right? Centripetal force, centrifugal force is getting changed, velocity is getting changed, right? And each and every point it is getting it is going to fill 9.8 meter per second square kind of acceleration, and in that way guys its velocity is getting increasing and increasing and increasing due to this acceleration. And the same thing guys I am trying to do here in the momentum. Yeah, so so it will try to change the previous stages as well. So basically it will always try to consider a momentum of previous stages. Now so here also if we were trying to consider those things, in that case I can say that my optimizer will be a better optimizer, and keeping those things in mind people have developed a different kind of optimizers based on the concept of momentum. So see, so people have said okay fine, so again these are the things that is happening already in the physics, so why don't we are going to adapt the same thing, right? Maybe it will try to give us a good result. And keeping those things in mind, they have introduced this concept of momentum. And according to this momentum, so there are various optimizers that we are going to get from their sides, and we have just started with the SGD with momentum. So there was a SGD, right? A stochastic gradient descent that we are going to use, right? So guys, in that case we are going to use this SGD. This SGD was getting navigating ravines, right? This kind of things, because again here in terms of a SGD what we are trying to do, so we were going with a single iteration, and for a single iteration we are going to get this kind of zigzag curve for getting converged to a local minima point, right? This was the thing that was happening in terms of a SGD. So what people have introduced, so people have introduced okay fine, so try to introduce here a concept of momentum. So momentum is a method that helps to accelerate SGD in the relevant direction and dampens oscillations. See, whenever you are going to iterate with these things, whenever you are going to converge all of those iterations into a a local minima point, so there is a very huge possibility that okay fine, so it will it is taking a huge amount of timing. So okay fine, so try to introduce here a concept of momentum. And in that way guys, they were trying to adding a fraction gamma of the update vector of the past time step to the current update vector. So see what they have did, they have just used that particular equation. See this is the equation. So theta will be theta minus bt, right? Bt. So in our previous versions, previous optimizers, we are doing the same thing. So theta will be theta minus something, eta into something, right? Some changes here. That learning rate into that change will be a single parameter, single term, Vt, and this Vt is getting defined as this one. So Vt will be what? So Vt will be gamma into Vt minus 1. So see here, gamma into V and t minus 1. So t minus 1 means what? And this t means what? So see here, this t means that tth iteration or maybe a current iteration, right? And t minus 1 will be one iteration before, or one earlier iteration, or one previous iteration, or maybe our one previous iteration. Yeah. So Vt will be what? So Vt will be gamma into V of t minus 1 iteration, right? Plus eta into delta theta into j theta. This particular term is same. What people have did, people have just introduced this Vt minus 1 and this gamma parameter. And what is the actually meaning of introducing these things, guys? So see what they have did. So they say that okay fine, so we are adding here a momentum term gamma. momentum term gamma we are going to introduce here, which means that, so this gamma will be having a value between 0 to 1, right? Its value will vary between 0 to 1. So they are saying that, okay, fine, so we are adding here this gamma, which means that I am only considering 90% from older weights instead of taking 100%. So see, so people were again arguing that, okay, fine, so if we are going to consider the older weights, so how much amount of older weights we are going to consider? Maybe 100%, maybe 50%, maybe 10%, how much? So this particular amount is getting represented by this gamma factor. This gamma will be having a value between 0 to 1, or maybe a value between, this will try to say, okay, fine, so you are going to consider maybe 0.9, maybe 0.8, maybe 90%, maybe 10%, maybe 20%. So whatever value it will be having, in that amount we are going to consider the older weights. And where is the older weights? So this is your older weights. This Vt minus 1 is your older weights. Means that what? So means that your Vt minus 1 means that your weights from your previous iteration. And how from previous iteration? So see how these things are happening, guys. So see, in a very first iteration, right? In a very first iteration at t will be equal to 0. In that place, this particular quantity will be 0. Right? Agreed? Because t minus 1 will not be available there. And when there will be not any kind of t minus 1, because this is only our first iteration. When we are just going to start our iterations, when we are just going to start our learning, so in a very first iteration, this will be going to be equal to 0. Vt minus 1 will be 0. So whole term will be equal to 0, and in that case we are just only going to give a kind of a constant parameter here. And the same thing that we have did in terms of SGD will be given. But now here there will be some kind of learning rate that we have utilized, this eta. This is similar into the as we have in our SGD. Fine, for a very first iteration. Now in our second iteration, we will be having this Vt minus 1. In this second iteration, this Vt minus 1 will be the learning rate from our first iteration. Whatever learning rate we have used in our first iteration, that will be our Vt minus 1. Now we are going to introduce our gamma. This gamma will be having any value, maybe 0.9, that people have introduced maybe in SGD. That okay, fine, so this gamma will be equal to 0.9. So we are going to multiply 0.9 into Vt minus 1, and this particular thing is getting added to this number, this term, and this will be equal to Vt, and this Vt is getting subtracted through from this older weights, and in that way we are going to update. Now in a third iteration, the learning rate, this Vt minus 1 will be the learning rate from our second iteration. In next iteration, this Vt minus 1 will be learning rate from our previous. So see what people have did. People are not going to introducing learning rates from each and every previous epochs. No, for each and again there will be multiple earlier iterations has been already happened. So they are not going to introduce each and everything. So what people have said that okay, fine, so here what we are trying to do, here we are considering the previous iteration, previous epochs, previous whatever weights we have learned. So we are just only going to consider those things. And they were saying, okay, fine, so this previous is depending upon the previous, and that previous will depending upon its previous, and in that way previous will depend upon the previous will depend upon the previous, and in this way so on. Each and every earlier iterations will depending upon their previous iterations. And this type of thing they are going to introduce in terms of a SGD with momentum, where this gamma was equal to 0.9, which means that I am only considering 90% of the older weights instead of taking 100%. And in that way SGD with a momentum has been introduced, and we get a smooth convergence of data and takes very less time to calculate the gradients. Yeah. So see, this is SGD without momentum and this is SGD with momentum. So some kind of a smoothness we are going to get here, guys, right? SGD with momentum. Now after this there is a Nesterov accelerated gradient akka nag optimizer. So see, there are multiple optimizers again, and we should know about each and every one, because again if you are going to choose these things, so on your thorough knowledge, whatever things whatever things you know about these optimizers, those things will be very much important and you have to move in that way. So guys, this is Nesterov accelerated gradient akka nag optimizer. So what actually this is trying to say, so people have people have introduced this new different kind of optimizer. So what they have did, so see here, a ball that rolls down a hill, a ball which is rolling down a hill, so it will try to blindly following the slope, is highly unsatisfactory. We would like to have a smarter ball which has a notion of where it is going, so that it knows to slow down before the hill slopes up again. So see, actually what is happening here and what people were thinking. So see, just try to focus over my words. See what was happening. So suppose if I can go with some kind of graphs maybe, then I think it would be better for me to explaining these things, right? Yeah, fine. So suppose this is our hill, this is the hill, and through this hill a ball is slowing down. So people says that okay fine, people have said that okay fine, so this ball is rolling down towards the hill, towards this particular ground surface, fine. Now this ball will try to move, it will try to roll blindly, right? It will not having any idea that where it is going. It don't know where it is going, and it is not having any kind of idea that where I have to go. It is just going to follow the trajectory, just going, not trajectory, it is just going to follow the gravity, or following the slope very much blindly, don't have any idea about where I am going and where I have to go. So it will just try to rolling down on this particular slope blindly. It will not having any kind of idea. And see, whenever this will getting rolling down, so after reaching at this particular stage, it's a kind of nature that there will be some kind of acceleration in this particular this particular point. From here there will must be some kind of acceleration, some kind of gravity pull which will getting applied over the ball, which will try to move this ball faster, which will try to give a kind of velocity, a kind of acceleration to this particular ball for moving towards the earth surface. Now this ball has getting a kind of a velocity, and due to this particular velocity, this particular ball has achieved some kind of a momentum, some kind of maybe a kind of a what I can say, a kind of a impulse, and all those things will result that whenever this ball will try to achieve at this point, it will not stop here, it will try to go up on this particular curve, right? It will go up on this particular curve again. See, whenever we are talking about this kind of a curve, this kind of maybe a hill, this kind of a ball, that is fine, there is no any wrong, there is nothing wrong with it. But see, just try to compare these things with our optimizer, with our gradient descent kind of algorithm. So there we are trying to shift our error factor on our minima point, means that there our error factor is the ball, see, and this is our minima point, and we have to shift down this particular minima point on this particular, sorry, this particular error factor on this particular minima point. Now whenever we are going to use this gradient descent kind of algorithms, there we are going to change these things. We are going to shift this particular point, and it will try to come down towards this curve. It will try to come down on this particular place. But what is getting happen? So sometimes there would be some kind of a huge possibility that, okay, fine, your error factor is coming towards this point, but it will try to go upward. There is a very huge possibility, right? So people were saying that, okay, fine, so it's fine if we are having a smarter ball which will try to stop itself if it is coming here, right? If the ball is coming here at this point, so see, whenever you are traveling inside a train, so suppose again we all have traveled inside a train. So whether your train is moving with a speed of maybe 110 kilometers per hour, or maybe 120, 130 kilometers per hour, maybe 160 kilometers per hour, or maybe people from China or Japan, your train will moving with a speed of maybe 300 kilometers per hour, 400 kilometers per hour. So see what is happening there. So when there is a stoppage, there is a junction where your train has to be stopped. So if that particular place is just nearby, your train will not try to increase its speed, or it will not try to continue its speed. It will try to decrease its speed, because if there is a junction which is just which is just after 2 kilometer, and your train is moving forward with a speed of 120 kilometers per hour, so see what will happen. Your train will not going to stop in just a 2 kilometer if it will try to move with this speed, right? So if your train have to stop after 2 kilometer, it must have to reduce its speed, and in that way, unless and until it is not going to reduce its speed, it is not going to stop. It is not going to stop at that particular point, that particular junction. So guys, in the same way, our ball has to stop here, our error factor has to stop here. And if our ball has some kind of idea, if we are having some kind of idea that, okay, fine, we have to stop here, we don't have to move further, that will be not good for us. So in that way, that thing will be much more beneficial for us. And guys, keeping these things in mind, people have introduced a kind of a nag optimizer, akka Nesterov accelerated gradient optimizer, nag optimizer. Now let's see what is this. So this nag optimizer, guys, so we uses our momentum term gamma into Bt minus 1 to move the parameters theta. Computing this gives us an approximation of the next position of the parameter, a rough idea where our parameter is going to be. We can now this one see. Same thing is going to happen here, and again we have changed slightly our equations, and in that case we are going to stop our gradient descent. We are going to do some early stopping kind of things, and in that way we are not going to move forward, and we will be going to achieve a local minima kind of things. So what people have did, people have used the same thing, gamma into Bt minus 1, that we have seen in the terms of a SGD, right? And this is also same, right? This is also same. So Bt will be gamma into Bt minus 1. Gamma is again 0.9. So yeah, gamma to value of around 0.9, right? Eta, this one. Now here in terms of equations they have changed. So here in terms of equations they have subtracted this gamma into Vt minus 1, this particular term, or maybe this particular term, from this theta. This theta is fine, there is no any issue with this theta, but they are trying to subtract this gamma into Vt minus 1 term from this theta, and this will be our loss function now. And introducing this particular thing inside your loss function, people have released a new version of optimizers, a new kind of optimizer which is known as Nesterov accelerated gradient optimizer, akka nag optimizer, right? And again, this nag optimizer is a kind of a very smarter optimizer which will be giving a very good result. So see, this is a kind of a nag optimizer curve. So it will try to move forward, but when it is going to reach at this particular point, it will be having some kind of idea that okay fine, now we have to move, we have to stop, and then it will try to take a turn. And in this way, this particular optimizer is going to work again, guys. So again, in terms of a theory, there is a lots of things that is not possible here in the class, but again, just try to think about the simple concepts that what is going inside this nag optimizer. So nag first makes a big jump in the direction of the previous accumulated gradient, brown vector. So in the very first beginning, it will try to make big jumps, right? A big learning rates. Measures the gradient and then makes a correction, green vector. Good. This anticipatory update preventer are going to fast number of tasks. So see, again, people have introduced a lots of different things, and those things have been termed as a nag optimizers. Here we are able to adapt our updates to the slope of our error function and speed up as in turn. We would also like to adapt our update to each individual parameter to perform C. So again, these things are fine, and in this way your I can say your nag optimizer is going to work. So try to keep this particular equation in your mind, and how this nag is going to work. Remember this particular concept, right? Again, people is not going to ask about this nag optimizer, but again, if there will be a question, we just go in this way. And again, guys, after this nag optimizer, again, this all optimizers, there will be a function. You can directly use all of those things by importing them from class library or maybe TensorFlow library, and then it will be getting used. Now there will be a ADA grade. Its name is Adaptive Momentum Based Gradient Descent Optimizer, or ADA grade. What is this ADA grade, guys? So ADA grade is an algorithm for gradient based optimization which adapts the learning rates to the parameters using low learning rate for parameters associated with frequently occurring features, and using high learning rates for parameters associated with infrequent features. So it is well suited for dealing with a sparse data. So see, now after this nag optimizer, guys, people have introduced a new kind of optimizer which is ADA grade. This ADA grade is a kind of a gradient based algorithm which is used for optimization, right? Now it will try to adapt the learning rate. It will try to change the learning rate as per the demand, right? So it will try to use the low learning rate for those parameters which are associated with frequently occurring features, and there will be some features also which are not going to frequent not going to occurring too much frequently. So they are going to assign a low learning rate for those parameters which are associated with frequently occurring features, and a high learning rate for parameters that are not frequently that are not occurring frequently. So whenever we are talking about a sparse data, so in a sparse data, again in a terms of NLP, we are going to deal with some kind of a different data sets. So there this particular ADA grade is getting used much frequently, right? A sparse data is a kind of data where we have lots of mixed data or mixtures of data, or in other words, data is not even and there is no any common pattern in between data. So in case of a sparse data, ADA grade works well. So see, again, if I can talk about a pictures, if I can talk about maybe a kind of a textual data, again, there will be some kind of patterns. In some cases there will be a similar kind of pattern available, but in some cases data will be too much mixed. There will be huge mixtures of data available. So guys, in that way there is a huge possibility that there will not be any kind of a common pattern available between the data, and in that case that data will be known as a sparse data. And for a sparse data you can use ADA grade optimizer which will work well. Now in a very beginning, we starts from a high learning rate, and gradually as I will increase my iterations, I will keep decreasing my learning rate, because in very beginning our neural network will not be aware about dataset and every time receives new variances or records of data. But in later stage, once my neural network is able to pass data for certain epochs or iterations, and so my model has already adjusted the weights, and if there will be some change not frequent, we will slow down the learning rate. So see, people have said that, what people have said, so in a very beginning we will be not having any idea that okay fine, so what is the how our data is, and how much learning rate, what is the learning rate that I have to give, right? So we are not having any kind of idea about these things. So in a very beginning people have just started with a very high learning rate, and gradually they are going to increase their iterations, they were keep decreasing their learning rates, right? Because in a beginning they don't have any idea, but as the epochs are getting progress, they are going to progress with some kind of iterations, maybe 10 iterations, 20 iterations, then they will try to decrease their learning rates, right? And in this case they are saying that okay fine, so we are providing our model a better possibility to converge for optimizing the losses. And keeping these things in mind, people have introduced this ADA grade kind of optimizer. Now they are saying that okay fine, so I will be able to define the accuracy of my model if it will converge, and in this way we uses to keep changing the learning rate and will not use a constant learning rate throughout the entire learning period. So what they were saying, they were saying that okay fine, so maybe in our all of the earlier versions of optimizers we are just going to use a kind of a constant learning rate, but here in this point of time, here in this optimizer we are not going to use that constant thing, constant learning rate, but we will try to keep changing this learning rate as as we will try to progress in our throughout the entire learning period. So it will be keep changing. A constant learning rate may not be suitable for all parameters. For example, so what they were thinking, so they were thinking okay fine, so if we are going to give a constant learning rate, there is a huge possibility, it may be possible that okay fine, so there are it will not be suitable for each and every parameters, right? So for example, some parameters may have reached the stage where only fine tuning is needed, and some parameters need to be adjusted a lot due to the smaller number of corresponding sample. So there will be a different kind of mixtures of data available inside your data, and in that way guys, if you are giving a constant learning rate, that will not be fine. And in that way we need to give a kind of a dynamic kind of a learning rate, which will try to change itself as per the demand, as per the requirement, as per the records, as per the parameters, right? So ADA grade was the first optimizer that people have introduced in this case, and again this was a very good optimizer for these things. Now ADA grade proposed as an algorithm that adaptively assigns different learning rates to various parameters among them. Yeah, see, in NLP there is a globe word. So globe word embedding uses ADA grade, wherein frequent words require a greater update and frequent words require a smaller update. So see, in terms of NLP we will be going through this globe word embedding, and in that case we are going to use these things, use this ADA grade optimizer too much. Now ADA grade eliminates the need to manually tune the learning rate. So see guys, whenever we are going to do any kind of a learning of neural networks, so in that case guys, we need to give some kind of a learning rates from our side, from our end, and in that case as a human being we don't have any idea that okay fine, so how much these things are going to happen with what learning rate it will try to converge faster, or it will try to converge in a better way. We don't have any idea, and in that case guys, this was a big problem, a major problem. And in that way guys, I think ADA grade has ADA grade was trying to take a complete breakthrough in this one, and here it have eliminates the need to manually tuning the learning rate. And so if I can talk about this ADA grade optimizer, so this look here people have given this particular equation. So wi plus 1, so I is the current iteration, sorry, I is the iteration, where I plus 1 will be the newer iteration, I will be the current iteration or maybe older iteration, and here wi plus 1 will be, or w new will be w older minus eta upon a square root of gti plus epsilon into gti, right? Now this is the learning rate, this is the partial derivatives, or this is the change or derivative, whatever you can say, maybe your derivative that you are going to calculate, right? For your changes, there will be a this one, there will be a parameter, this one, and this will be a GTI. There will be a epsilon parameter, a smoothing parameter. See, WI will be your older weight. GTI will be, this GTI will be a squares of gradients from previous epochs. See, as we all were talking about the momentum concept, so here there is no any kind of thing regarding gamma. There is no any gamma kind of thing. But what people have did, so people have calculated the squares of gradients from previous epochs. So whatever previous epochs we have did, whatever previous epochs, for from each and every previous epochs, they have collected each and every gradients, they have squared them up, and that particular term is known as a squares of gradients from previous epochs, which is known as GTI, right? GTI. So this GTI is the squares of gradients from previous epochs, and in that case, here we are going to calculate our new weight, our new weights for our new iteration. So we are not going to, we are not going to give here a kind of a constant learning rate. Again, eta will be there, eta will be a kind of a constant thing, it is fine, but we are not going to give only a eta, but here we are trying to divide this eta with this particular value, and this particular value is what? So this is I can say this is a summation of this GTI plus epsilon. So this GTI will be what? This GTI will be a squares of gradient from previous epochs, and this epsilon will be a hard coded value, and its value will be 1 into 10 to the power minus 8. So this type of things we are going to add, sum them up, and then it's we are going to do its a square root, and this particular factor is getting, we are going to divide our constant learning rate with this particular value, and in this way, guys, we are going to regularize, we are going to keep changing, we are going to give a kind of maybe a allowance, a capacity to keep changing this learning rate as per the demand, as per the iterations, and this will be just our derivatives. See, so the main focus is this particular factor, where we are trying to call the concept of momentum, and again we are going to utilize this particular epsilon. Now people says that if GTI is equal to 0, if this will be equal to 0, system will go for a toss. How? So see, here we are going to give you a epsilon kind of a parameter, which is known as a smoothing parameter. Suppose we are not giving here a epsilon, and in that case, if this GTI is going to be 0, so a square root of GTI will be what? Any idea? A square root of GTI will be what? Any idea, guys? Okay, fine. Try to search over the Google. What will be the value of a square root of a 0? So if this GTI will be equal to 0, system will go for a toss. And avoiding these things, people have did here two things. First of all, they have introduced a square root kind of operation, that if this is going to be equal to 0, so again whatever GTI we are trying to take, so we are not using it directly, but we are trying to perform its a square root operation, and after a square, so see, after doing its a square root, so this particular thing will getting used, so that is fine. But if this GTI is going to be equal to 0, in that case there will be a very huge issue for you, and you will not be able to converge for any point, and that will be a very big issue. System will go for a toss, and for avoiding those things, people have introduced here a epsilon kind of a parameter, or a smoothing parameter, which will try to smoothen, which will try to give you, if this is going to be equal to 0, this will give you some kind of a value, and then you will be able to give any kind of a numerical value here after doing the square root operation, and in that case you are going to get something here. If this particular thing will equal to 0, this learning rate will become what? This learning rate will become undefined, right? Undefined, and in that case you will not be able to do anything and your system will go for a toss. So these are the things very much important. Now, how this adaptive momentum based gradient descent optimizer has been happened according to the research paper. So I have given here a diagram. You can go with this one. You can try to understand each and every steps, and you can go with these things, right? Now there are some kind of disadvantages in ADA grade optimizer. So here in terms of ADA grade optimizers guys, the learning rate is monotonically decreasing. The learning rate is monotonically decreasing. So here people have introduced a very high learning rate in a very first place, and then they have decreased these things in as our iterations is getting progress. But this is a kind of a cons. This is a kind of a disadvantage in terms of a ADA grade optimizer, that our learning rate will be getting monotonically decreasing, and for a very long epoch we will not be able to train our things. The learning rate in the late training period is very small. So yeah, if our learning rate in a very late training period will be very small, then in that case we will not be able to learn anything, and then there will be not any significance, there will be not any importance of doing this kind of a learning, right? It requires manually setting a global initial learning rate. So in a very first place we have to give it a kind of initial learning rate. This eta will be given by us. So computationally very expensive. Yeah, again computationally it is expensive. So these are the 4 different cons that is available inside ADA grade optimizers. Now after this people have introduced a different kind of optimizer, which is a ADA delta optimizers, guys. Now after this ADA delta there will be a RMS prop, then there will be a ADAM. So after ADAM there will be a ADA max optimizer, there will be a NADAM optimizers, and there is also a I can say AMS grade optimizers also available. So guys, there are lots of things available. So again, it's not possible to explain each and everything in just a single class, so I think I have to keep these things here till this point. So in a tomorrow session I'm going to start with ADA delta optimizers, then I will come to RMS prop, then after RMS prop I will be moving towards ADAM optimizer, which is a very good one, and then there will be 2 more optimizers which will be your maybe ADA max. So how your ADA max is getting worked, so maybe in terms of ADA max I'm going to explain these things, and then after guys ADA max there will be I can say NADAM also available there. See, this is Nesterov accelerated adaptive moment estimation NADAM. NADAM means that NAG plus ADAM, NADAM. So this type of experiments that people have did, and again in this term we are going to get a multiple kind of optimizers which we can try to use as per our requirements, as per our need, guys. Okay, fine guys, so I think this is all from my side, and I think these all classes will be too much important if you are looking for making a career transition into this field. So just go with this theoretical things. Maybe after some couple of classes, maybe 2 classes or maybe 1 classes, we will be in a position to do some kind of a practical, right? So just stay here, stay tuned here, and try to learn each and everything. And again for this notebook, today you will get this notebook after getting this video. So just try to watch this video until last, and then I'm going to give this particular notebook it's a repo link in this description, right? And then from that one you can get these things. Okay, fine guys, so this is all from my side. Now it's time to sign out from here, and then We will meet later in tomorrow's session. Okay, so goodbye, take care.